Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Alright, good morning everybody. Welcome to my presentation. Today I'm going to talk about part of my thesis work on internet distance prediction. By distance, we mean the latency between internet nodes. So such distance information can be very useful in many applications. For example, we can use the distance information to select the closest server from multiple replicas, or to select the closest neighbor if we wanted to build a topology or overlay network. So certainly we can use measurement to get such distance information. But if we use measurement, it's likely that we're going to incur a larger measuring overhead for the network. And if we have a lot to measure, and also if we wanted to update such measurement over time. So prediction is an alternative to measurement. Prediction can provide approximate distance information using a small number of measurements. Suppose we have 1,000 nodes, and we wanted to know the pairwise distances between them, which is 1 million. So the goal of prediction is to use only, for example, 10 to 15,000 measurements to get a distance estimation of the 1 million distances. So in recent years, there have been quite a few approaches proposed for internet distance prediction. So most of them use a coordinate to characterize the location of a node in the internet. So if we wanted to know the distance between two nodes, we can estimate it using their coordinates in the coordinate space. And this category includes GMP, Lighthouse, and the more recent Vivaldi, IDES, etc. So meanwhile, other systems such as ID maps and Meridian use a measurement-based infrastructure to infer such distance information. So in this work, we focus on coordinate-based distance prediction. In order to get the coordinate of a node, first we need a number of specialized nodes called landmarks to serve as reference points. So in recent years, people have found out that the selection and the placement of landmark nodes is an important factor in the quality of prediction. So given the landmarks, the coordinate of node can be computed by trying to minimize the prediction error, which is the difference between the predicted distances and the measured distance from this node to the landmark nodes. And these techniques can be used for this purpose. So before we go further, let's first look at an example of how coordinate-based distance prediction, such as GMP, works. Suppose we have a number of landmark nodes distributed over the internet. So first, they pin themselves and get the pairwise distance between themselves. So based on such measurement, in the coordinate space, we embed themselves into such a coordinate space. And each of them will have a coordinate, and such coordinates are calculated by trying to match the predicted distances in the coordinate space with the measured distance in the internet. So now suppose we have an ordinary node. What it does is it pins this landmark node and get a measurement of its own distance to the landmark node, and then similarly will position itself in the same coordinate space. And this node will calculate a coordinate locally, similarly by trying to match the predicted distance with the measured distance. So similarly, if we have another node, a random node here, it will first measure its own distance to the landmarks and then position itself in the coordinate space by calculating a coordinate. So now, if we wanted to know the distance between these two nodes, instead of using direct measurement, we can approximate it using their distance in the coordinate space using their coordinates. So the objective of this work is first to evaluate the prediction accuracy of all these prediction algorithms that have been proposed so far. And we also wanted to study how the application can react to the prediction inaccuracy. And finally, we want to study how can we improve the accuracy of distance prediction. We're looking at different possible techniques of improving prediction accuracy. So first, we use experiment to evaluate the prediction accuracy of distance prediction algorithms. We evaluated 3 representative algorithms, including GNP and 2 other algorithms, triangulated heuristic and IDAS. We use 3 internet measurement datasets. The first is from the MIT P2P SIM project, and the second is from Cornell Meridian project. And both datasets use a KIM method to measure the pairwise RTTs between internet nodes. And the third one is from the active measurement project. And for the first 2 datasets, the short distances can be very short, and the long distance can be very, very long. But the majority of nodes will, have a medium length from about 50 milliseconds to 200 milliseconds. So the accuracy of a distance prediction algorithm has oftentimes been measured using the relative prediction error metric, which is the absolute prediction error normalized by the measured distance. So here we show the prediction accuracy using relative prediction error of GNP prediction over the 3 datasets. So on the left side, first we show the cumulative distribution. We can see that the curves go up very quickly. This means the majority of the links can be predicted with a decent relative prediction error. But all these 3 distributions have a long tail. So if we break down the relative prediction error over different link distances, we can see that short links tend to have high prediction error. So from both graphs, we can see that the AMP dataset here has the highest prediction accuracy than the other 2. If we compare the P2P SIM and the Meridian dataset, we can see that the Meridian dataset experiences lower prediction error for the short distance range, but for the medium and long distances, the Meridian dataset actually will have higher prediction error. So in addition, we have also studied the impact of such prediction inaccuracy on the performance of applications. We have studied different applications such as overlay multicast or general overlay construction. And here we show the results of using predicted distances to select the closest server. And we measure the stretch metric, which is actually the distance to the closest server if we use prediction versus the distance to the closest server if we use measurement. Here we show the results from all 3 distance prediction algorithms. We can see that all 3 achieve very similar performance. Actually, in our experiences with other applications, it's harder to say which one is the best from the 3. They perform similarly to each other. So in the rest of the presentation, I will focus on the results from GNP prediction only. So for comparison, we also measured the result of using random selection. And we can see if we use prediction, then we can improve a lot over random selection. But if we compare it with the optimal result, which should be 1 in this case, there is still a huge gap. And this gap is bigger as the number of candidates increases. So actually, this picture summarizes our experiences with all the different applications we have evaluated. That is, if we use prediction, it is certainly better than nothing, but it's not good enough, and sometimes it can be far from being good enough. Yes?
So distance to closest server based on prediction, that means you use prediction to find what you think is the closest server,
yes,
and then actually measure the distance to it, the time, the latency to it, and compare that to the closest server. Okay, so this number is going to be greater than 1?
Yes,
greater
yes.
than or equal to 1. Why does it grow as the number of servers increase?
So intuitively, as the number of servers grows, it's easier for you to make a mistake or a bigger mistake by using prediction. Okay, so yes.
Another question might be, so what are the absolute values of the delay? So for example, if one server is a microsecond away and the other server is 10 microseconds away or a millisecond away, that's a stretch of 1,000, but it doesn't actually matter for any application whether it's a microsecond or a millisecond.
Yes. So that's why we are using the stretch. I really want to find out the ratio between.
No, I'm saying stretch is sensitive to this. My question is, what's the distribution of the actual round-trip times?
In particular, in the previous graph, you showed that the error varies depending on the link distance.
Yes.
So that's going to affect the link distances between the servers is going to affect what this graph is going to actually show.
Yes. So actually, in this experiment, we use the P2P sim dataset. What we do is we randomly select a number of nodes as the servers in this case, and then we ask the rest of the nodes to pick the closest one among these servers, and we measure the error they make based on prediction. So yes, you are right in that the dataset itself, the distribution of the distance in the dataset itself will have an effect on the absolute value here. So.
Okay. Did you look at that? I guess so. My statement is going to be that stretch is not a good metric to use because it's very far away from what an actual application cares about. An actual application may care about sort of a very discretized binning time, where all servers within about 5 milliseconds away are effectively the same. And then if it's sort of 10 to 50, that's another sort of equivalence class, like that, rather than looking at stretch, which is very sensitive.
So let me try to understand your question. So what you are saying is, in reality, the servers will be about the same distance from the client, or
that if there are a number of servers, all a very small distance away from the client, then choosing the non-optimal server might result in a very large stretch value, but actually no perceptible deficit in performance.
Yeah, if all of them are equally bad or equally far or equally close, I agree. But maybe you are right. The reality of the servers will actually have such a distribution. But think about it this way. So what if these are not actually web servers? Think of it in the scenario of building an overlay network, and the servers can be the possible candidates for I want to select a neighbor that is close to me in the overlay network, and you have a bunch of other candidates scattered over the internet. I guess our data set probably is better characterize this situation. It's not probably not the servers in terms of servers, but as overlay neighbors.
I don't see your point, but let me not deliver your point.
Okay, sure. Okay, so next we started to study what's behind such prediction accuracy, why we cannot predict accurately. So going back to our experiments with all these three data sets, if we look at the density distribution, we find out actually the distribution is similar, but the P2P sim, compared with P2P sim and the Meridian dataset, the AMP dataset has a much smaller range. So for the P2P sim and the Meridian, the maximum distance is close to 1,000 milliseconds, but for the AMP dataset, the maximum is only 373 milliseconds. So here we propose a conjecture that the distance range has a significant impact on the prediction accuracy. So if you have a narrow distance range for the dataset, we are more likely to have a more accurate prediction. And this is sort of intuitive, right? So it's hard if we have to position this node accurately relative to both nearby and the distance node. But if all the distances are more uniformly distributed over a narrow range, it's easier for us to predict, to do embedding, to do a prediction. So at the meantime, we have also observed a second interesting association between the distance density and the prediction accuracy. So here we show, on the left side, we show the density distribution of P2P dataset. And on the right side, we show the distribution of relative prediction error over different link distances. And we can see here that the high density errors correspond to the low prediction error. So this says the high distance density distribution will also contribute to high prediction accuracy. So intuitively, okay, so the process of actually, for coordinate-based prediction, the process of calculating the coordinate is a process of optimization, and the target function is a prediction error. So if we have a high concentration over a certain area, then the optimization over this area will achieve better results. So this is just to give an intuition behind this. Okay, so far we have all the prediction accuracy or inaccuracy. We have shown the magnitude. And now we wanted to look at the direction of the prediction error, whether it's underestimated or overestimated. Here we measure the directional prediction error. So in this experiment, what we did is we first group all the distances into groups of 50 milliseconds. And then in each group, we measure the distribution of prediction error. And here we can see that the short distances are likely to be overestimated. And for the longer ones are likely to be underestimated. So this has an important implication in that there is such an interference between the short distance and the long distance in that if you wanted to choose the shorter distance, but the shorter distance is overestimated to be long, and the long distance is underestimated to be short. So we are more likely to mistakenly take the long ones as a short one. Okay. So far we have seen that the prediction accuracy is not consistent over the distance spectrum. So some distance ranges are likely to experience a higher prediction error than the other ranges. And also our previous slide shows there is a potential interference between different distance ranges. So we next propose new metrics to measure such effect. So here the range accuracy measures the prediction accuracy for a given range. So we look at those links that are actually within this range if we use the actual measured distances. And from them, we count how many of them are still here based on prediction. So here we show the range accuracy of using GMP prediction over all three data sets. And in this experiment, we measure three ranges, which is from 0 to 20, 0 to 40, and 0 to 80. And because the AMP dataset has the highest prediction accuracy and it has the highest range accuracy. And if you still remember, the Meridian dataset has a higher accuracy than P2P same dataset. So the Meridian dataset will also has higher range accuracy here. So on the other hand, we also propose reverse range accuracy. So in contrast to range accuracy, the reverse range accuracy will look at those links that are within this range if we use prediction. And from these links, we count how many of them are actually within this range. So this metric measures the interference from other distance ranges if we use prediction. So we have also measured the reverse range accuracy of GMP prediction over the three data sets. So AMP is the best. It still has the highest reverse range accuracy. But the opposite is observed here for P2P SIM and the Meridian dataset. So although the Meridian dataset has higher prediction accuracy for the short distances, but it also has worse prediction accuracy for the medium and long ones. So these links are more likely to be predicted to be short, to make the reverse range accuracy actually lower than P2P same dataset. So is this clear? Oh. All right. So far we have evaluated the prediction accuracy of different distance prediction algorithms, and we have found out that the accuracy is not sufficient, especially from an applications point of view, such as closest server selection. And our evaluations have also found out that the prediction inaccuracy can vary for different distance range, and there exists potential interference between short and long distances. So next, we'll look at how to improve distance prediction accuracy. We'll study different ways of doing this. So first, we'll look at to use measurement with prediction. So second, we'll study alternative landmark selection schemes. And finally, we'll propose a new hierarchical prediction approach. Yes?
So, get back to the question on the
Yes.
basics about this prediction case. So how do you decide the dimension and the location of the coordinate?
That's an interesting question. So basically, when you do a prediction, actually you can control the dimension for your coordinates. So people have found out that we don't need a high dimension for the internet.
That's possibly due to overfitting, right?
Can you?
Like when you have higher dimension, then it's harder. The training set is not.
Yes, exactly. If you use a higher dimension, then it's like you have more variables to calculate. But if you go too far, that will probably have a bad effect on your process of embedding.
So what's typical?
So actually, I did some experiments on this. I tried from 2 to 3 dimension and also higher dimensions. And beyond a certain point, actually, it doesn't help. As you said, it doesn't help. Actually, it can make it worse. So in this experiment, we use a dimension 8. In our experiment, we used 8 dimension. And this is also consistent with some other previous work on distance prediction. Yeah. Questions?
Are you going to discuss RBC1?
Yeah, that would be the rest of the talk. Okay, so first we look at a more application-specific problem. That is, our problem is to select the shortest link from a candidate pool. Actually, this problem is very common in many applications, including the closed server selection and to select close nearby neighbors in building overlays. So the intuition is like this. If we have a candidate pool of 100 links, if we use prediction, probably we're not going to find actually the shortest one using prediction only. But what if we selected 10 or 20 of them? There is a good possibility the shortest one will be in this 10 or 20. Or if not, at least we can find one that is pretty close to the shortest one. So, so more precisely, here we use prediction to pre-select the candidates. And then we measure these pre-selected candidates to find out the best one. So this is a very simple approach. But the problem now becomes how many do we want to measure? And we use a adaptive measurement scheme. That is, we can always start with 10, 15 measurements, and then we can proceed with very small batches of 5 measurements each time until the improvement from further measurement is too little. So how much does measurement help with selective measurement? So for this purpose, we have experimentally compared selective measurement with random measurement. So here, suppose we can perform as many measurements as we want, and we measure the distance to the closest node as we use more measurements. Here we can see that the selective measurement using prediction to pre-select the candidate, the result converges much faster than random measurement. So this shows that the prediction does help us to effectively narrow down the candidate pool.
What's the horizontal axis?
The horizontal axis is the percentage of measurements we perform.
Out of what population?
Oh, okay. So this experiment, this picture, is using the P2P SIM dataset. So the P2P SIM dataset has about 1,700 nodes in total. So what we do here is, for each node, we look at all the other nodes, and now we want to find out which one is closest. And for the selective measurement, is first to order these other nodes based on predicted distance, and we measure them to find out the closest one based on this ordered list. So here we show a percentage of measurement instead of the absolute value.
So each node is trying to find the closest among the entire set of nodes or among a selected set of server nodes?
With all the other nodes.
So one means you're looking at 1,700
Yes.
measurements?
Yes. So we are using this dataset just to want to find out, what if we have a huge candidate pool, what happens? How many do we have to measure? I know in the reality we are not going to be faced with such a problem of selecting the closest one out of 1,700. This is just to show what happens if the candidate pool is large.
And the distance, the closest node is the distance to what? To the node that you think is the closest to the...
Okay, what happens is we order the nodes based on the distances, predicted distance. And here the y-axis shows the distance to the closest we have found so far. For example, we have measured the first 100 closest based on prediction. And we found out, for example, if we found out the closest 10 milliseconds.
That's the actual distance?
Yeah, the actual distance. Okay, so as we can see that this both curves goes down very quickly, and there's a knee point for both curves, and beyond which point, even if we use more measurements, the result only improves very slowly. So let's take a closer look at this same picture, and we can see that if we use selective measurement, the knee point is very close to the origin. So actually, we only needed to perform only 1 or 2% of measurement in order to get a good result.
Do you know what the actual value is of that curve?
It's about from 10 to 20 measurements if we map it to absolute numbers.
10 to 20 measurements in a set of 1,700.
Yeah.
So the selective range, you use some kind of prediction to select those nodes?
Yeah, first you look at the predicted distance and order them in terms of their predicted distance. And we wanted to measure the shortest one first, as predicted.
The other order, basically from set to node, selection algorithm, select a number of nodes, basically try to clean and measure the distance.
Yes.
So randomly, you just randomly pick a number of nodes in the set and try to see which one.
Yes. For the random selection, we don't have prediction information, so we just randomly.
So why would it monotonically increasing for the random one? Because in the random one you might choose and make mistakes, right? So you don't expect to see the curve.
But right, you measure more, you are going to find out a better result.
This is the closest one among noise.
Yeah.
Right, but for example, usually you select 50. These happens to be pretty large or something, right?
Yeah. This also assumes that latencies aren't there's no jitter in your latency measurements. Right? So this assumes a stable network.
For this data set, it's also 1,700 nodes. One or you actually nodes and then the average.
Yeah, actually in this experiment we repeated for every node, and then we take the average here.
Okay, so this one curve is actually the average distance to cross.
Yes, yes. But for each specific node, we will see a similar curve like this.
Understand.
Yeah, but this curve here is the average of all of them. Okay, so in addition to the selective measurement scheme, we have also studied other techniques. For example, alternative landmark selection schemes. So in recent work, people have found out if we select some nearby nodes and landmarks, we will be able to improve the prediction accuracy for the shorter distances. So it's also intuitive in that these nearby landmarks will help us to position this node more accurately relative to these nearby nodes. But in our study, we use both synthetic and measurement dataset. We found out that it is true the shorter distances will be improved, but the other distances, such as medium and long distance, they are most likely to experience a worse prediction accuracy. So here we show our results using hybrid landmark selection. That is, we use both nearby nodes and random nodes and landmarks. And we can see that the overall prediction accuracy is actually worse compared with using random landmark selection only. So this.
So how do you find the nearby?
How do you find the nearby? So what you can do, I mean, in reality, so in our data set we have global knowledge. We know which one they are nearby. In reality, what you can do is, for example, you have a sample of the other nodes in the system, and then you have to do some pin to find out which one is closer. Okay, so if you look at the result of using hybrid landmark selection, and if we measure the range accuracy and the reverse range accuracy, we can see that, okay, the hybrid landmark selection can improve the shorter distances. So if we measure the range accuracy over these short distance ranges, we're going to see improved range accuracy. This is good. But if we look at the reverse range accuracy, we can see that the hybrid landmark selection actually resulted in a worse result here. This is because, okay, shorter ones can be better predicted, but the medium and the long ones are more likely to be predicted as short. So this is bad. Actually, in our experiences with these different landmark selection schemes, it looks like no matter how, it's very hard for us to find a universal scheme that can achieve a decent prediction accuracy over the different distance ranges. So we further make a conjecture here. This is because we are only using one coordinate for each node. So if we use only one coordinate for each node, it will be hard for us to position this node accurately with relative to both nearby and the distant node. And also remember, we have made the observation that if we use a small distance range, then the prediction accuracy are likely to be higher. So based on these observations, we further propose a hierarchical approach. So instead of using only one coordinate for each node, we use multiple coordinates. And each coordinate positions this node at a different distance scale. So each scale is like a level in the hierarchy. So in level 0 is a global scale. So the level 0 coordinate can be used to predict any distance with a decent quality. And each succeeding level in the hierarchy represents a decreasing range. So the intuition is this lower level coordinates will be more accurate for predicting the distance that are within the range of the current level. So what do we do during prediction given two nodes? So we wanted to choose the right scale or the right level in the hierarchy to do the prediction. So here we show an example. Suppose we have two nodes, and each of them will maintain global coordinate. And in addition, for example, this green node will also maintain an additional coordinate for those distances that are within 100 milliseconds to itself. And similarly for this red node. So So here, the distance between these two nodes are beyond 100 milliseconds. So in this case, the distance between them should be estimated using the global coordinates. So on the other hand, if they are indeed close to each other, in this case, they are within 100 milliseconds to each other. So the distance between them, in this case, should be estimated using the local coordinates. So, okay. So, yes.
So you will have like this type of circle for each of the levels, I can assume. Like global will be like infinite, but other than that, each level I can assume that one set of one set of coordinate which is within that range.
Yes, conceptually. We can think of it that way.
And each node therefore establishes a set of different landmarks at each level.
That is actually one of the hierarchical schemes we have proposed. We are going to discuss two different hierarchical schemes, and what you are talking about is the second we are going to discuss later. Okay, so first we are going to look at a different hierarchical scheme. That is, we use a hierarchy of landmark nodes for all the nodes in the system. So here we show a two-level hierarchy. So the level 1, or level 0 is a global level, and the level 1 is a local level. So at the level 1, we have 3 landmark groups, and the landmark nodes in each group are supposed to be close to each other. And the centers or leaders of these landmark groups will join the higher level, in this case level 1. So given this landmark hierarchy, so each node maintains at least one coordinate at each level of the hierarchy. So here we have a green node, and this green node is closest to the center cluster group here. So this green node will calculate a coordinate for itself relative to this center landmark group. So during prediction, then we have 2 levels here. To which level should we use? We use a bottom-up approach. We look at the starting from the bottom level. If these 2 nodes, they are both close to the same landmark group at this level, then we can assume that they are close to each other at the range of the current level. So we can use our coordinate relative to the same landmark group they share to do the prediction. So here, suppose we have another red node, and it is also close to the center landmark group. So this red node will have a coordinate relative to this landmark group. So during prediction, we can use their coordinates relative to this landmark group to estimate the distance between them. So otherwise, okay, so suppose the red node is not here. It's actually closer to the right landmark group. So at the level 1, the red node will maintain a coordinate relative to this set of landmarks. So now, if we want to predict the distance between these 2 nodes, then we cannot use their level 1 coordinates anymore. We have to move up the hierarchy to use the next higher level coordinate to do the prediction. In this case, we use the global level coordinate. Yes?
So to make the hierarchical level, you don't use any prediction algorithm. You have some kind of data based on that you decide the hierarchical level? Yes.
The hierarchy, in practice, we're thinking one possible way of building this hierarchy is we follow the hierarchy of the internet. For example, we can deploy a number of landmarks for each subnetwork. So in our experiment, I will show you the next slide. We actually use a heuristic to select these landmarks to build the hierarchy from our data set. So, yes.
For example, in M and N in your graph, are you going to tell us how M knows when it wants to estimate the distance to some node and which level it should use? In other words?
Yes. So everybody. Okay. So when we do a prediction, we use a bottom up. We start from the bottom level. In this case, we started from level 1. So we first look at if they share the same landmark group at level 1.
But my question is, how does M know based on just the name of n, which landmark group it might be using, right?
Yeah.
Because obviously,
Sure.
they
I
do
understand.
that.
Okay. Right. So this is okay. So generally, if you want to predict the distance between two nodes, you have to know the coordinate of the other node at least, right? That we can assume we have to know something about the other node. For example, the coordinate. So here, in addition to so each node has at least one coordinate at each level of the hierarchy. So we need to know, okay, here is the coordinate for the random node at level 1. Here is the coordinate at level 0. In addition, we need to know, okay, which landmark group is this coordinate with relative to. These are the information we would need in order for this purpose.
You basically assume that all of the coordinates and all of the landmark group information is global information. Is that a fair statement?
Okay, I agree. So it is true that this landmark hierarchy is global. Everybody needs to know this hierarchy in order to calculate its own coordinate. But during prediction, for example, the green node needs to know the coordinate information of node n. That is, I don't know if you should call it global or not.
It seems like for every server that I want to do prediction, I then have to know its coordinates.
Yeah, that's true.
Seems like global information.
You can think of it that way. If it's a server, when you publish, okay, the address, the IP address of the server, you could also publish here. Here is the coordinate of this server. If in that way, you can say it's global. But in other applications, if you wanted to build an overlay network, you only need to know the coordinates of your candidates.
In this particular scheme, the set of landmark nodes is itself, the list of landmark nodes and landmark groups is itself global information,
Yes.
with each landmark group having a well-known name, and any node can look up that name and figure out who the actual landmark nodes are for that group.
Yes, the hierarchy information is global information in this case. Yes. So, okay.
So,
Yeah.
How does M know what landmark group N is using?
So this information comes with the coordinate. So you know node n. You have to know here is node n's coordinate, and this coordinate is with reference to this group, landmark group.
Which group?
In this case, it's the right group.
How does M know its reference? The coordinate is in the right groups.
This information comes with the coordinate of node n.
So each group has a name, and N tells M, here's my coordinate, and is with respect to the group.
Yeah. Since since the hierarchy is global information, so we can assign a name or identifier to each landmark group. Okay, in order to evaluate such a shared landmark hierarchy approach, we have built a two-level landmark hierarchy for our experiments. So the level 0 is a global level, and at level 1 is a local level. And level 1 has 16 landmark groups, and each has 16 landmark nodes. So we have 256 nodes in total. So we use such a heuristic for selecting the landmarks from the dataset, because for the dataset, we have no idea who these nodes are. All we have is a huge distance matrix. So what we do is we randomly select the number of nodes as C. And we should select, if we wanted to build, have 16 landmark groups, we select more than 16 of them. And given these Cs, we started to grow the groups, and one node each time. And each time we select the closest node from the remaining nodes to join the current group until we have 16 in each group. Then now we have a number of groups as candidates. Then we can select the best of them to actually build the hierarchy. For example, we can select those groups that have the lowest diameter, for instance. So next we'll look at the prediction accuracy in terms of relative prediction error. And we compare the hierarchy approach with using random landmark selection and hybrid landmark selection. And we break down the relative prediction error over different distances. We can see that the hierarchical approach can improve the prediction accuracy for short distances, but with similar prediction accuracy over medium and long distances. And but for the hybrid, we've already seen that it's good for short ones, but for the longer distance, it can be really bad. So now let's look at the impact on range and reverse range accuracy. So we can see here that for the range accuracy, because the hierarchical approach can improve upon short distances, the range accuracy is higher. And if we look at the reverse range accuracy, the hierarchical approach can still improve upon the random landmark hierarchy. But in contrast to the hybrid landmark selection, the reverse range accuracy actually can deteriorate. Okay, so now we also studied a different hierarchical approach. So instead of using a global shared landmark hierarchy, here we allow each node to choose its own landmarks. So at the global level, we still need to share the same landmark nodes, but at the local level, each node has the flexibility to choose its own. So here the hierarchy is more virtual. So we don't actually have a shared hierarchy. The hierarchy can be defined by smaller and smaller distance range. So during prediction, we have we first estimate a range for the distance, and then we use the smallest enclosing range to predict the actual distance. So here is the example. So suppose at the global level or level 0, we still share landmarks. So each node will compute a coordinate relative to the global landmarks. And in addition, for each node, for this node, we'll select a number of other nodes within 100 milliseconds to itself, and using these landmarks to compute a local coordinate. And similarly, for the red node, it will also select a number of nodes within 100 milliseconds and compute a local scale coordinate. So this is how the second hierarchical prediction scheme works.
In this case, how do you determine the initial set of landmarks? Is it the same type of start with a very large random set and just paying until you find some, or is there some?
You mean for the global level or?
No, the local level.
For the local level. Okay. So one technique we can use here is like I said before, we have to do some measurement to find out which ones are actually using 100 milliseconds. Suppose we have a sample of random nodes in the whole network. We can progressively ping until we find enough number of them to serve as local landmarks.
But that could take a long time in a large data set.
I mean, for each node, I mean, if you have to do this for each node, then probably will take a long time. But each node, if they can do this locally, then probably it won't be so bad.
But each node, if you select a given node,
yeah,
that node needs to try with other nodes.
Yes.
So this node needs to same thing, because if he waits for the 10 selection, he needs to do more, because there could be some other node which are closer to them, closer to that given node. That should be part of this step.
I'm not sure if I fully understand your question. So you are saying if I wanted to find landmark nodes within 100 milliseconds, but I found someone that is only 10 milliseconds with me, it will be fine. It's still acceptable. Right? So that's what you are saying?
Yeah, but like if you find, like if you want to make a landmark set of 10 nodes, and if you ping 10 and you found 10, but there could be some other node which should be part of this landmark set.
What do you mean by should?
Because that maybe the distance may be less than or within that 10 millisecond range.
Yeah. So I suppose, given a data set, and for each node, okay, potentially we can have many nodes that are within 100 milliseconds in this case. But we don't care. We only need, for example, 10 of them. We don't need to find, which criteria should we use? To choose the best ones from all those. It's not important, as long as they're within 100 milliseconds to me. They will be good enough for the purpose of being landmarks. Oh, yeah.
Does that mean that if I have suppose where the end node is on your picture there, suppose that there's another node that's very near. It may choose a different set of landmarks within that same 100 millisecond circle, or it'll choose the same ones.
That's possible. So in our experiment, we do not control they should overlap or not. So each node makes local choices. So in some cases, it may end up another node very nearby happens to choose the same set of landmarks. That's possible.
But it may choose a completely different set. It may choose a completely different set.
Yes.
How does that?
So,
I'm sure what you call them landmarks.
what do you suggest we call them?
Well, I don't know. It just seems kind of different than.
Yeah, I'm tired of this landmark here, landmark there. If we can come up with different names, that'd be great. But for each node, there are still reference points. There are still landmarks.
But you use landmarks just to do the initial bootstrapping of that coordinate space, right? Are you proactively then, as other nodes come online, shaping or changing your landmark set, or are you just assuming that once you've chosen a set of landmarks, then you leave that's what you choose?
I think we should leave them alone once we've chosen them. Otherwise, there would be a consistency problem. Because, after bootstrapping, the coordinate of every other node would be referenced to this landmark set. If we change it, it can become a different coordinate space.
But nodes are going to come and go, so you've already got that problem anyway.
Yes, each node does choose different landmark nodes. But I'm saying here is we should not change the bootstrapping.
Well, the landmarks don't come and go, do they?
Very good.
Yes, landmarks come and go.
Oh, are those peers?
Yes, they're like peers. So as long as they have a coordinate, so as long as they are within 100 milliseconds, they qualify.
When landmark leaves, your coordinate space is already getting disrupted anyway.
What do you mean disrupted? So there are, think of it this way. Think of the landmarks like a base vector in a multidimensional space. Okay, originally we have 10. And these are for bootstrapping. So, and now each node will have its own 10. So if one of the original 10 leaves, as long as each node still have 10 local, it doesn't matter. The coordinate space does not depend on the node to be alive. As long as we have the space established, what I'm saying is, as long as we have the space already, we don't care if the original bootstrappers are still there.
Let's take this one offline.
Okay. Here, this further. Okay, so now we don't have the shared landmark hierarchy anymore. So how do we estimate a range for each distance? So for the shared landmark hierarchy, we can tell from if they share the same landmark group. So for the second hierarchical scheme, so how do we do that? So we propose a anchor-based range estimation. So these anchors, they are similar to landmarks, but they have a special purpose here. That is for the range estimation. So the selection of the anchors should have a good coverage of the network. Ideally, we want each node to be within some distance to at least one of these anchors. So how do we do range estimation? We use triangle inequality. So suppose here we have an anchor node, and we have two nodes, green and red. If both of them are within R/2 range to this anchor node, then we can estimate the distance between M and N is below R. So of course, it's obviously the accuracy of such range estimation depends on two factors. So first is the coverage of anchors. If two nodes, in this case, if these two nodes are actually close to each other, but there's no anchor node inside, in this case we'll assume they are far away from each other, which is not true in actually. So the second factor here is the triangle inequality. So this recent study has found out the violation rate of triangle inequality typically is 10 to 20% on the internet. So in the majority cases, we can still expect it to be valid. So next we conducted experiments to evaluate the accuracy of such anchor-based range estimation. So here we use a three-level hierarchy. The level 0 is a global level, and the level 1 covers distances of up to 40 milliseconds. Level 2 covers distances of up to 20 milliseconds. So in practice, again, the anchor selection we can use, for example, we can deploy a number of anchor nodes for each subnetwork. But in our data set, we use a heuristic to select the anchor nodes. It goes like this. So first, every time we select a random node from the data set, and we accept this node as an anchor node if this node can cover at least two more nodes. Okay. This anchor selection actually needs a parameter which is the radiance. Here we use half of the level 2 range, that is 10 milliseconds for the anchor selection. Okay, that is, if we have a node which can cover two other nodes with 10 milliseconds, we'll take this node as the anchor. And here in this table, we summarize our evaluation results with both data sets. So we can see that these anchors have a decent coverage for level 1, but the level 2 coverage is only for the P2P data set is about only 50%. So this can be a potential problem. And if we measure the false we have measured both the false positive and the false negative. So if we look at the blue columns, the false positive for both data sets are pretty low. So which is good. That is, if we estimate it to be short, it's most likely it's going to be short. But the bad thing is it has a high false negative. That is, this link is actually short, but we estimate to be long. So this will have a negative impact on this hierarchical prediction schemes, because if we estimate the short to be long, then the short distance cannot benefit from the higher prediction accuracy of the smaller scales. Okay, so next we'll look at the prediction accuracy of the second hierarchical approach. So first we show the relative prediction error. Okay, similarly we'll break it down over different link distances. And similarly we can see, compared with using random landmark selection, the hierarchical approach can improve over short, and for the medium and long ones achieves similar as a random landmark selection. But for the hybrid ones, hybrid ones is good for short, but for the longer ones can be bad. So if we look into the range accuracy and the reverse range accuracy, here we can see that the range accuracy can be improved using both hybrid landmark selection or hierarchical prediction. But here our hierarchical prediction achieves similar as random landmark selection, but the hybrid ones will have a lower reverse range accuracy. Okay, so for this second hierarchical approach, its performance has a critical factor, that is the accuracy of the range estimation. So our table has shown that we're we have actually a quite high false negative rate, which is bad. So we wanted to find out how this range estimation inaccuracy affects the performance of this hierarchical approach. So for this purpose, we apply an oracle here. Suppose we know exactly the range for this distance, and we see, the result with the oracle is showing the black lines here. We can see that compared with the optimal, the hierarchical, there's still a gap between our hierarchical approach and the optimal. So actually, how to improve this range accuracy, estimation accuracy is part of our ongoing and future work. So we wanted to study how can we improve this range estimation accuracy. So in summary, in this study, we have first evaluated the accuracy of distance prediction algorithms that have been proposed so far. And we have found out that their accuracy is not good enough, especially from an application's point of view. And for the more specific application of selecting the shortest link from a candidate pool, we have proposed a selective measurement scheme, which uses prediction to narrow down the candidate pool. And this selective measurement scheme can actually find a short link with a small number of measurements, even if the candidate pool is of large size. So our studies have also found out that the prediction accuracy can vary a lot over the distance spectrum, and there exists a potential interference between short and long distances, and such interference can have a negative impact on the performance of application. And we have illustrated this impact using the range accuracy and the reverse range accuracy metrics. And our results of evaluating different landmark selection schemes have shown that we can, if we select nearby landmarks, we can improve over the short distances, but we are going to suffer for the longer distances. So based on these studies, we observed that it probably is fundamentally difficult to predict both short and long distances if we use only one single coordinate per node. So based on this observation, we further proposed a hierarchical approach which positions a node using multiple coordinates and multiple scales. So our evaluation results have shown that we can actually improve the short distances with very little impact on the other distance ranges. Yes?
Have you or anyone else looked at the stability of predictions over time as, say, internet routing changes?
In our experiments, we didn't, because we actually, so in the real internet, we probably have to update the coordinates so over time, because the real distance can change. But in our experiments, we use the measurement dataset, so only look at this dataset. They don't change. So.
Has anyone done a longitudinal study over time?
So I know Professor Eugene at the Rice University, and he first studied the GMP prediction, and he also worked on how to build a real prediction system, which is called NPS. So basically, in his study, the coordinates actually can be updated over time to reflect the real distance change.
The question is going to be, so with this kind of hierarchical scheme where I'm actually selecting subsets of landmarks, is that more or less susceptible to changes in routing? I mean, would you expect, if there were changes in routing over time, would the whole hierarchy have to be regenerated, or?
Okay, so for the first hierarchical approach, which uses a shared landmark hierarchy, so it's possible that the hierarchy, some nodes can go or just leave. So we have to maintain such a hierarchy over time. And for the maintenance of the hierarchy, as long as, so requirement for the hierarchy for each landmark group is the landmarks in each group are close to each other. So if this is violated, we will have to update the hierarchy. Yeah, and the same, I guess, with the second hierarchy scheme. if this landmarks goes beyond, originally it's within 100 milliseconds, somehow it's 200 milliseconds, we probably want to update it as well.
And is that any harder than sort of doing updates that I would have to do if I just had a single flat coordinate system? Here's my concern. My concern is that with a single flat coordinate system, basically like the GNP system, as routing changes, some individual nodes may have to say, look, I need to rewrite my coordinates now. But individual nodes can do that on an individual basis, and as they update their coordinates, predictions to distance to them get more accurate. Here, a routing change can cause a disruption to the hierarchy that effectively caused everybody to have to go and re-update everything before any predictions have accuracy. Is that true? Is that worse? Is this a practical problem or not?
It depends. I mean, if the at the global level, everybody shares the same set of landmarks, right? This is also true with GNP. So GNP uses a global set of landmarks. So what happens with GNP will happen here. So we have additional problem with the lower level landmarks. So but under the local level, this problem, I guess, is going to be more localized. If one landmark group has some change, it will affect some nodes in the system which are close to this landmark group. So that is true. So some of the nodes will probably have to update the coordinate because this landmark group is updated.
So would you argue that this system actually be better in terms of stability over time because, crossing our fingers, routing changes probably are less likely to take a group of nodes close together and tear them apart rather than different ends of the topology than it is to take nodes.
Something close doesn't that mean that they're physically close. It just may mean that they happen to be a high-speed link that could go down.
Well, I mean, the way round trip time is being measured, it's actually propagation delay. So what it really is think wire feet distance, right? I mean, the metric here is minimum round trip time measured over multiple things. So link capacity isn't an issue.
No, but they may be physically far apart, but still be connected by relatively high-speed router interconnects.
I think that's not an issue because bandwidth doesn't affect propagation delay.
Less queuing time.
Less queuing time, right? Well,
maybe Sandeep is saying queuing time is a main component of the round trip time.
Oh, okay.
So therefore, high-speed link may.
Yes.
If you find the minimum round trip time between the two peers, then this time is more propagation.
So the way all these round trip time measurements are done is they take the minimum over many, many samples and assume that.
So the queuing delay is So what happens is, I think, in reality, I mean, the distance or the latency between nodes, they are not going to be very consistent over time. As long as they are, not way off the chart. For example, this measurement is 10 and the next measurement is like 200. It's okay. I mean, if it's between 10 and 15, probably it's still acceptable. We don't have to adjust the coordinate responding to every little change.
But an AS level routing change really will cause some of these things to go from 10 milliseconds to 50 or 100.
Yes.
So in the presence of those kinds of change, right, where the actual routing topology is effectively tearing itself apart and throwing nodes that were close together in terms of wire feet distance to be very far apart from each other in wire feet distance. Can you make any predictions or make any statements about how you think this hierarchical scheme would work in that environment?
In that environment, as I said, as long as such drastic changes does not happen to the landmark nodes. For example, the landmark nodes in the groups originally they are 10 seconds to each other. As long as they are not suddenly the distance between two of them 100 apart, so we don't have to do anything with the hierarchy, with the landmark hierarchy. But when that happens, yes, we have to update it.
But you studied this at the level of having two levels of hierarchy. Why two? Why not
5. And what happens as the number of levels of hierarchy increase?
Okay, so the essence of this hierarchical approach is we wanted to improve the short distances without affecting the long distances. So in our experiment, for example, with the shared landmark hierarchy, the 2-level suffices. If we use more levels in the hierarchy, okay, so the higher level in the hierarchy will correspond to longer distances. But so based on our observation of the dataset we use, the medium length links, they can already be predicted with decent accuracy. So we probably don't want to bother with these medium links.
I have the feeling that in the hierarchical approach, there are different coordinates for different levels. Somehow currently you cannot merge the different coordinates together here. So at level 0, you have one coordinate. At level 1, you have another coordinate. Currently, this coordinate is not linked.
No.
So for this particular reason, not plan coordinate. If you have too many coordinates, probably won't help that much. In a sense, you're using one coordinate for range, using another coordinate for longer range.
Right. I'm just wondering whether, if you go back and look, there's still a fair amount of error in the short distances, even with the hierarchical scheme. It's better, but it's still got a substantial amount of error. So I'm wondering whether adding more levels, there's a trade-off there, right? Adding more levels intuitively should help you do even better with very short distances.
Yeah.
But I also suspect you're going to end up with very unstable coordinate systems because your landmark latencies are going to be relatively short. Right? You're already at 100 milliseconds, so doing a 10 millisecond radius is probably not all that useful.
I think it depends on your application. If your application server or super node is so close, you can really compute at those distance.
Then maybe it doesn't matter if you've got error.
Okay, so one thought here is, okay, if we indeed have many nodes in a very short distance range, then if we just do random landmark selection, then even if the short distances will have a decent accuracy. Here, okay, of course, we can refine the bottom level here to be not a 20 millisecond. We can use a 10 millisecond level or 5 millisecond level. So it probably will make sense in reality, but just in our data set, we probably don't have this many links that are actually this short.
And this goes back to the earlier discussion about whether it even matters at that level. If you're dealing with the difference between 4 milliseconds and 5 milliseconds, maybe nobody cares.
Yeah, as long as it's not from 5 to 50. Okay, so the result of our work has been published in these 2 papers. So the first paper summarizes our study on different distance prediction algorithms and the impact on applications, and also we also have the results on selective measurement. So the second paper summarizes our results on hierarchical distance prediction schemes, and all these papers and other papers will be available on my website. So in addition, okay, as I worked on other different projects, if the time allows, I can go through this list. So first, I have worked on the monitoring and management of large-scale distributed system. So the goal of this work is to deploy a large-scale application as fast and as reliably as possible. And we also worked on the self-healing property. That is, when some nodes fail, how to recover these nodes as quickly as possible. And given after the system is deployed, the nodes will be able to monitor the health and other performance statistics between themselves. And in this project, we use P2P technologies.
Could you mention some key technologies in that project?
Yes, sure.
This project from some other
project?
All right. So in this project, we for the deployment part, we emulate a virus propagation. So basically, first we have one node in the system, and this node will infect a second node, and now these two nodes will infect two other nodes. So it's like it is fast because the speed is exponential, and also after the deployment, they will be able to monitor each other. If some nodes fail, then other nodes will recover them. So, so the key here is because it's P2P. I mean, we don't have actually a centralized component to take care of the deployment or the monitoring. So the P2P style contributes to our to the fast deployment and self-healing functionalities here. So in addition, I have worked on cooperative media streaming. So in this project, we look at the on-demand media streaming, and more specifically, we look at the cache and the relaying approach. That is, each node can buffer the media object locally for a short time. So a later client, when it comes in, it can stream from these other clients instead of going to the server. So in this project, we look at the content discovery problem. So how these nodes find each other. So we propose a self-organizing and decentralized overlay network. So to enable these nodes to find the potential streaming sources, and also our overlay network is topology aware. So if there is a streaming source that is nearby, we are going to go to this streaming source first instead of going to another faraway one. We have also studied how to use data encoding schemes, different data encoding schemes, to adapt to the client-side resource heterogeneity and to add more resilience to failures. So the next project is content-based publish-subscribe system. So there are two basic approaches to publish-subscribe. So one is content-based, and the other one is subject-based. That is, we can group the content into different subjects. But the content-based will describe the content or the user's interest in a more expressive way. For example, we can assign, we can use different attributes, and for each attributes we have certain different values. So in this project, we study how to use the concept of virtual subject in content-based publish-subscribe. The problem is the content-based publish-subscribe is great from the user point of view, but there is a potential problem is there are going to be a high content matching overhead. So if we can find out the common interests between the clients and we group them into virtual subject, then content is published. It only needs to be matched once at the entrance point of the group, and then forwarded to the rest of the group without further matching. And also, we can, if in each group, if we can find out such a path that it's forwarding only without branching off, then we can replace it with a shortcut. So our approach is able to eliminate both redundant content matching and forwarding operations in the publish-subscribe system. So the next project is on P2P search. So in this project, we look at how to improve the efficiency of P2P search in unstructured P2P networks. And we propose to use a partial index. So instead of indexing every data object each node owns, we build an index of peers' interests only. And also we maintain pointers to those data that are unpopular in the system, that are harder to find. So this partial index can be used to build the overlay network such that each node is connected to the other nodes that share similar interests. So if a node comes in, you want to find out other nodes that also have similar interests to me, it can ask this partial index and connect to these nodes to join the overlay network. And this partial index also has a second use, that is, if we search the overlay network, we didn't find what we want, and we can ask this partial index for some search hints. We can ask this partial index who else has registered this data as our interest or as an unpopular data. So, okay, so I've also worked on how to enhance the overlay routing infrastructure, including anycast, multicast, and unicast. So anycast is, suppose we have multiple replicas in the network for the same data or the same service. So anycast allows the client to find a close one. So we have observed that the locality-aware structured overlays is actually a natural environment to implementing anycast that we have, and we have actually built anycast into one of the locality-aware overlay networks pastry. And in the multicast project, we propose a hybrid of forwarding path and reverse path multicast. I know it's okay. So this work is based on the observation that in a structured P2P system, the routing path is oftentimes asymmetric. That is, if you look at the routing path from overlay node A to overlay node B, it's most likely to be different from the routing path from node B back to node A. So in pastry, if you look at the routing hops, we are going to see from the source to destination, we are going to see from short to longer and longer hops. So the same from B to A. So it's going to be short and long. So what we do here is we combine the short hops from both paths to build the multicast tree. Okay. So for the unicast, we look at how to improve the routing performance in terms of either the number of hops or the routing latency by using the built-in redundant routing information. So in addition, I have worked on how to use P2P technologies for resource management. For example, how to do automatic resource discovery across different domains. For example, this would be useful for in a grid computing environment. And that will be all. Thank you.